Ms. Atkins, you have called parcel 005, Ms. Atkins.
I started with 8 because I looked at the work. Like I looked at the work that I did, and then I was like, something's not adding up here. But 0 is there, and 0 happens to be the answer I got. So I'm liking what I'm saying. Or maybe I think actually when I used the 1/2, I got like 0.5 or something, and I was like, that's pretty close to 0, but that's also close to 1. Because I was looking at my paper, looked at my work, and I like wrote up my little formula, and I did my 1/2, because my answer was like, it was like 1, but then I slipped in my little 1/2 thing, and I was like, something ain't adding up here. Or I got.
So you got half emotional.
Huh?
You got half emotional.
Yeah, and then, at the time, it doesn't really make sense now, but at the time I was like, oh yeah, I guess that could be possible. Yeah, I think maybe it has half of a valence because this one's only a single bond and this one's a double bond, so it's like what that's meaning.
See how I figured that fucking the thing, like the sheet, onto my white paper and then like flip it over. So I have the whole table.
That's some finesse work. I'm not even gonna do math, that's just smart. I was over there and I was like, what's the bond angle of this one? I was like, BF3 bond angle? Thank you, sir, I appreciate that. Statistically, she could have guessed the minute 50, like probably. Well, no, that's not true, because they weren't just like true false questions. Yeah. Because he does that little thing where he puts like 6 of them.
She basically did yes.
Huh?
Yeah. She basically did yes.
Yeah. I mean, it is what it is. Apparently I don't. Because I walked up there and he was like, how many valence electrons does an oxygen have? And I said 8. And I was like, oh. That's it. That was really bad. Of course, Todd and Liam had ruined the curve.
Attention students, there'll be no baseball workouts today. No baseball workouts today.
Play baseball?
Did you really like my phone? I had to take this thing off. I walked in there and I was like, whoa.
Because you never know.
He was like, my sister did it on rose colored, so I was like, okay. I didn't expect it. Oh my, you kidding. I can feel it literally color.
Hey, John. Hello, Ryan.
I think we'll probably
Yeah.
because if we said break functions, you have to change it. Like there's no way you would make like 20 questions in this order. Because those take like
I read for 40. That's gonna be rough. You better not be taking the test. We are. I'm done for it. Because like I lose sleep. I need more than an hour and a half.
Me too.
Exactly.
Yeah. This is a very.
We don't have the things that help us pass the class.
I did that one way too much. Sorry.
I mean, it's only 4 days, right? My time.
Have you used this way too much?
So I feel like we'll probably have Wednesday off, and if we do that, we probably get CS on Wednesdays. So we can teach the other 4 days.
I was like, yeah, I'm Johnson. Which one is quizzes? And she was like, no, that really sucks. Nothing. I'm just like, what?
I know, there's been so many people in every class.
Right? She could do a piece of it.
Exactly, isn't that like double the desk? Cram that around in there.
I did.
I hope physics is still a small class.
I think it was 6. What rank is it? 4-2?
Yeah. I'm not even worried this class is gonna be massive. There's 20 people in there now, and 20 people in the other class. We're gonna have like 8 people at every bench. We did bench and squat. We were gonna do it yesterday as well, but we couldn't because
Actually, she wasn't really.
that's what I was
one
gonna
day that
do.
we
But
had.
then I just watched the show the all through.
And she was like the one club. Well, I was legitimately confused about something. I had an actual
I wish
question.
I could do that.
And I was like talking to her. And she looked at me and under her head like she's like,
Well, good morning.
Good afternoon.
Hope we're all doing well. Who's ready for an easy day of calculus for a change?
I'm so ready.
It's not. It's not a joke. It is for real. This is what we're going to do today. It should be relatively easy for us. I changed, I did maybe play a little bit of a joke on you guys accidentally. This problem uploaded into Canvas for a little while there in the wrong slides. I didn't realize that until this morning. So I changed them over to the correct slides. So today we're going to do inverse functions, which is actually quite easy. Let's get our homework out from yesterday. Our 5-2 homework. 5-2 homework. I started trying to grade your Unit 4 test. I thought that was going to go quickly. I was wrong. They are not so good so far. I've only made about 4 of them in, and it took me about 25 minutes to do those 4. So, that's fine. Okay. Angie up here for the 5.2 homework. Let me go down a little bit so we can see the whole thing there. For the first couple of ones, that's 1 through 17. A couple of things for us to talk about here today. As we are getting started. Keyboard. Things here for us. Okay, so thing number one. Tomorrow we're going to have our first quiz for this unit. Sir? I did? Well, let me come check. I thought I had. So, where was I? Tomorrow, we're going to take our first quiz for this unit. Ideally, I'll be updating your grades over the next couple of days, so you'll be seeing some things kind of fluctuate. I think we talked about that briefly yesterday, though, right? End of the 9 weeks happened, so now I can start putting in some of your grades for this coming set here, looking at that, for us, that's going to be all of Unit 4 was kind of put back. So Unit 4's homework, Unit 4 tests, Unit 4 quiz, all going to be going in. At this point, I'm just going to wait till I get the test done, and then I'll put it all in at one time. So you have a quiz, test, and a few homeworks, 5 homeworks to be exact, going in all at the same time. Okay? What to expect there. Second thing to expect. Okay, so big announcement yesterday, right? We're all coming back to school April 14th, right? At least that's what the school board decided, for those of you unaware. Regardless of my individual feelings about it, let you know that what's going to happen for class is Mr. Kaufman's already made decisions because I don't have to cooperate with anybody as I'm the only person that teaches AP Calc in East Gaston. Class will remain as it is. We're doing new lessons every day. That ain't going to change. Homework's going to be due when I see you. So that means that every time I see you, you're going to have a homework assignment done. Just like normal, just like math 2. Just like pre-calc. Let's see. Quizzes and tests. You've done every quiz and test open notes with the calculator so far. I'm going to let you do them open notes with the calculator. That's not going to change. At this point, there's no point in trying to do something different, so that's what we're going to continue to do. The only thing is you should start to expect a time limit. On the surface as it is right now, I don't see us getting more than, realistically, a class period or 2 to do my test. So for those of you that have told me that you spent 4 or 5 hours on a test, you're going to have to start doing some more practice to be faster. Because you ain't going to have 4 or 5 hours to do a test. And the length of my tests are not changing. You have your notes. You have your calculators. My suggestion is to be more prepared. In exchange for that, of course, you will be taking them here, and you have the best resource, the guy who wrote it, at your disposal. So that should help balance a little bit out there. At the end of the day, gang, just be flexible with me, okay? We've been taking everything as it comes here, dealing with getting punched in the mouth time and time again this year. And things changing on a dime, and you guys have been good about it. And I know you guys well, both personally and academically. So you can just work with me, and I'll work with you guys. We're gonna make it see. We're gonna see through, and that's just what it's gonna be. By the time you guys come back 4 days a week, like legitimately, you got like 3 weeks before your AP exam. So we ain't gonna be doing a whole lot other than starting to prep for that. We might finish our last unit and then start prepping for our AP exam. If we have time after that, then we'll reapproach what we can do after, but that'll be our focus. Yeah?
How many units are we going to get to?
How many units are we going to get to? No idea at this moment. At least 6. That's my goal, is at least 6. We're gonna finish Unit 5 by roughly next week. So that puts us on pace to take the test and everything before spring break. What I'd like, Todd, is for us to finish Unit 5 free and clear before Easter break, and then perhaps take Easter break to recharge our batteries and not have anything to worry about or stress about, especially because I'm going to need that time to get ready for what's going to happen after. So either one way or another. Now, how that shakes out in total, we'll have to see, because I have no idea what's going to happen with the calendar, because I've been told that they might change some dates around for us. I have no idea what's going to happen over the next couple weeks. Nobody really does. But I can tell you we're going to finish Unit 5 for sure. And with whatever time remaining, we're probably going to get through at least Unit 6. Ideally, we can get Unit 7 in there too, which would be awesome, which is more than half of the curriculum, which is more than what I thought we would get. But at the end of the day, like I told you at the beginning of the class, this is a 145-day curriculum. And traditionally, I only get about 75 days to teach it. Less than that, really. And this year, it's been even less than that. So we're going to do the best we can, but right now, ideally, I'm hoping to get through Unit 6 and 7. Ideally, Unit 6 and 7. And then we'll have to reevaluate, of course, pretty much every week with where we're at. Because right now, if we don't have better grades in Unit 5 than what we have right now from Unit 4 quiz and test, we might have to pump the brakes on our pace and slow down a little bit, because I can't have you all getting C's and D's. And whether it's the material is too hard, we're not understanding, I didn't do a good job of teaching it, whatever it is, we got to go back and we're going to have to wait and see. Maybe Unit 4 was just a bad unit for us. Unit 5 will go better, but if Unit 5 is just as rough, then we're going to have to pump the brakes and go back and maybe do a little reteach of 4 and 5. Okay? So it's all by ear right now. It's a good question. I encourage you guys to think up other questions about class and things like that, so that way I can think about and form them. The better plan I have going into it, the better we can all be prepared. But right now, like I said, my goal is to make as little changes as possible to make this as smooth a transition as possible. I will tell you outright that your class is 18 students, and I already have 14 desks in here. Obviously, we won't be doing the live stream anymore, so I'll have Parker, your desk will be back up. Well, you can have that desk back, and there will be one sitting right here. So really, we'll be looking at adding about 6 or 7 kids onto what we have in here right now. Okay. So, albeit it ain't ideal, but my 4th period is 25 kids, and I have small classes. Miss Aiken's got a class of like 37. Yeah, she got like 18 on Monday, Tuesday, and like another 18 on like Thursday, Friday. So we're in pretty good shape. And the kids that will be joining, it ain't like you don't know them. It ain't like you don't know who's all in this class. Some of you work together, even though you're in different cohorts. That's fine. So, nonetheless, let's go ahead. Oh, I forgot to scroll down the answer key. My bad, guys. Let's scroll that down a little bit further. And there is almost the whole second half of it. Almost the whole second half, missing the last couple of problems there. While you check that over, I'm going to go ahead and pass this out. Tonight's homework for this lesson, I decided rather than doing something out of the book, I was going to print out this worksheet here for you all. This worksheet comes courtesy of Miss Willis. I don't know if you guys remember her. She used to teach here way back when. I think when some of you guys were freshmen, or maybe sophomores. She teaches college calculus now over at CPCC and gave me this worksheet, so big shout out to her. 1 through 10 is going to be our homework here tonight. I wanted to make sure I passed it out because I goofed earlier today. I forgot to pass something out to my honor student. So I'll make sure I pass it out to you guys. And let's scroll down just a little bit more so that way we can get the last answers in. There's the last 2. Do we have any homework questions we'd like to tackle together, go through, anything like that? Anne-Marie? 45. Okay. Anything else? 45 seems to be a pretty common question. 43, 45 and 43. 45, 43. So let's take a look at these two. Take a look at these two. (45) and 43. So we want to solve the differential equation, and we'll use a graphing utility to graph three solutions, one of which will get through this particular point. So let's go ahead. Let's start with number 43. We got dy dx is 3 over 2 minus x. So we have dy dx is 3 over 2 minus x. Okay, so what do we need to do here, gang? What do we need to do? Oh, and they gave us a point here, 1, 0. What do we need to do? What's going to be our first step here? Let's scroll up on our answer key here so that way we can see 43. Zoom in a little bit. Okay. So I have dy dx, right? I have an x and a y value. So I propose that first thing we do is get back to the original equation, which will require us to do an integral. So that's what I did to start with, is I did the integral of my function. That'll bring us back to our standard y value. That'll bring us back to our standard y value. That'll get me back to the original equation so that I can graph it. So, integral of 3 over 2 minus x. How do we want to do this integral here? I know it's on the board, but you guys should be able to look at it and tell me. We're going to set u equal to 2 minus x. 2 minus x, very good. If u is going to be 2 minus x, that makes du -1, correct? -1. So what I need to do here is first I'm going to take this 3 out like a multiplier. And I'm actually going to make that a -3, so that way I can bring a -1 in its place. And 2 minus x. That way we have everything set up the way we want here. Are we all comfortable with what I've done for my coefficients and my manipulation here? That's what you see there, of course. And then we'll go ahead, -3, we have 1 over u du. This gives us -3 of the natural log of the absolute value of u plus c. Or -3 natural log absolute value 2 minus x plus c. Are we all okay with this so far? Okay. Now, of course, this is equal to y. That was the whole point of doing this, is I had dy dx. I want to get back to y, so that way I can actually graph. Now, before I can graph this thing, I do need to find what c is going to be. Once I have that, then I can graph it, and then I can do all the stuff that they want me to do with the points. So, they gave me an x and a y. I'm going to plug them in and find c. So I have y here is going to be 0, -3, natural log of 2 minus 1 plus c. So we have 0, we have -3, we have the natural log of absolute value of 1 plus c. Are we all okay so far? All good? Okay. What's natural log of 1? 0. So I have 0 equal to -3 times 0 plus c. That means c must be 0 then, correct? Okay, so my actual equation would be y equal to -3 natural log absolute value of 2 minus x. Not x minus 2, 2 minus x. Throw it in decimals, graph it, and then we can look and see where it's across the x-axis and all those other things that they want us to do. Questions here? Honestly, once we get to here, we're good. Everything else from here should be relatively easy. Everything else from here should be relatively easy. Questions here about this? Concerns here for this? 45 is in the same section. It just involves tangent of 2 theta. tangent of 2 theta. So let's go ahead, let's take a look at this one. We're going to approach it in a similar mindset. It's just going to be the integral using tangent here. So going along with a similar idea here, we have tangent to theta. And the point in question here is going to be 0, 2. Okay, so we'll go ahead, we'll set up the integral here of tangent of 2 theta.
D theta.
Okay, what do we want to do here? How am I going to integrate this? I think the easiest thing would be u substitution for 2 theta, because you don't have a rule for that. You have a rule for tangent of a variable, but not tangent of 2 times a variable, right? So we'll just do a little u substitution right here. U is going to be 2 theta, which makes du just 2, correct? So I need to bring in a 2 multiplier here. So 1/2 on the outside, tangent of u du. Are we all okay? All comfortable? Yes? Maybe? I don't want to overwhelm us. We're all set? Okay? Let's integrate. I gave you the rule for this yesterday. What's the rule here for integral of tangent? Sorry. No, because I swapped that out for you. 2 theta and 2 d theta. So I took the 2 d theta and made du. Does that make sense? Yes, no, maybe?
So where did the 1/2 come from?
When I brought in my 2 multiplier. So let me put this step in here. So this is 1/2. 2 times tangent 2 theta d theta. These 2 make my du. This is being substituted for you. Does that help you guys see what's going on there? Okay. Okay, so the rule for tangent is very simple. We're going to have here, drawing a blank. Integral of tangent is going to be negative natural log cosine u plus c. So we have 1/2, or well, let's say negative 1/2, the natural log cosine of 2 theta plus c. Are we all okay with this so far? Provided that I did my work correctly. Yes. Okay. Now, plug them in. Well, of course, this is equal to y, right? And I have things to plug in, right? 0 and 2, we need to find c, just like we did last time. So I'm going to have 2n equal to negative 1/2 natural log cosine of 0 plus c, right? Okay, first let's get rid of this negative 1/2. Let's multiply everything by negative 2. That makes us negative 4. Natural log absolute value cosine of 0 plus c. What's cosine of 0? 1. And that gives us natural log of 1 plus c. Gives me c equal to negative 4. Equal to negative 1/2 the natural log of absolute cosine 2 theta minus 4. Use this as your general equation if you like. What did I do over there that I got something crazy? Oh, I solved that for theta is what I did. That's all. I solved that one for theta. Either one works. I'd use this one personally. Questions here? Okay. Let's move on to what we're going to do today. Let's move on to what we are going to do today. Today should be an easy day. Emphasis on should be. Now, some of you asked earlier if I was joking with today's lesson. I don't know if you were being serious, whether you thought that today's lesson is going to be hard or easy. Yeah, inverses should be ridiculously easy. Inverses should be ridiculously easy. There's what the Mr. Coffee here. And we'll get started. Or nobody wants a grumpy Mr. Kaufman without coffee. Grumpy Mr. Kaufman is no fun for anybody. All right, let's get into it here. Today we're going to talk about inverse functions, and then we're going to do calculus with inverse functions. Okay? So first, let's remind ourselves how to find the inverse. Let's find the inverse. So, going on to slide 1. How do we find the inverse? To find the inverse of the function, all we're going to do is switch domain and range. Switch the domain and the range. Since we are still going to be working with equations, all we're going to do here is switch x and y, or x and f of x. Typically, we're going to move out of our function notation to actually find this, this inverse here. Once we've done that, we'll resolve the equation for y, and we'll rewrite it as f inverse of x. I cannot stress to you the importance of writing clearly here, which I know is ironic coming from me, but it is really important that you write clearly here, because it's very easy to misread f inverse, which is f to the negative 1, as f derivative, which would be f prime. Okay? It is very easy to misread that if your work is not clear and legible. I will try extra hard today to be clear and legible. The standard replacement here is this is what I've taught in pre-calc and in math 3 when we've done this before. We're going to replace f of x with y. We'll swap x and y, resolve for y, and replace with f inverse of x. You guys should all be very familiar with this, as I've taught all of you how to do this in pre-calc, and no, none of you were here when I used to teach math 3. I know Ms. Rodriguez has taught this to you at the very least. So, let's just prove that we remember how to do this here. Let's go on to our next couple of slides. Let's work a few problems here. So let's go on here. We're on slide 3 right now. Let's go on to slide 4. And can you give me the inverse of this particular function? And we should be done. We're just about done. Who wants to do it? Ryan.
Is x plus 5.
X plus 5. Yep. Okay. Next slide. Try this one. Okay. Who wants to help out? Should be done. Done. X over 6 looks good to me. Okay, next slide. Okay, we should be done. John?
2x.
Okay, looks good to me. Next slide. Okay, Allie,
X over 4 plus 2.
let's find out. Okay, that looks good. Anybody do it slightly differently? There's another option here. I imagine that instead of distributing, you divide by 4, right? Okay, what if I distribute? I have x equal to 4y minus 8, right? So that's x plus 8 equal to 4y, x plus 8 over 4. Okay, so which one's right?
Well, they both are.
They both are. Why?
Because if you separate them before, it's just X over
Yeah, they're the same equation, they're just written differently, right? So this is something that you have to be, well, I got to be extra careful about because you could do the problem one way, Don could do the problem the other way, and you guys could have completely different looking answers, but they are equivalent, okay? At the end of the day, it doesn't make a difference as to which one you end up going with. However, once we start doing calculus with these, sometimes one way is more beneficial than the other. For example, something like this requires a quotient rule. Something like this does not, right? So this is where there is an advantage to doing them certain ways over others. There is no necessarily right, wrong, pattern way for you to do this. It's just case by case, situation by situation. Okay? Next slide. Find the inverse here. All right, then. We should be just about finished. Who wants to tackle it? I've heard from John, Ryan, Dom, and Allie. I believe the other ones of you have gotten involved yet. I can't believe that none of you are volunteering before I get to actually doing some calculus here. Parker,
3x minus 11.
let's find out. What'd you do first, Parker? Subtract 4?
Is it plus 1? I thought it was plus 1.
It is plus 1. My fault.
Yeah.
I got plus 1. Subtract 4, got x minus 4, 3, y plus 1.
And then distributed y plus 1 on both sides.
Send the x minus 4 back in its place is what I would do.
Yeah, I messed up.
It's okay. We might still get the right answer. Let's not give up on it yet. Send the 1 back over. This is what I'm looking at here for this one. That's what I'm looking at here for this one. Though, Parker, there is, of course, another way that we could represent this as well. We could put these together, but I don't think we're going to get that answer that you said.
Yeah, I don't know why I distributed.
Now, you could have did that. You could have distributed here. You could have FOILed this out. You would get xy minus 4y, x and minus 4, and just factor this y out. You're going to get x minus 4, and over here you have 7 minus x when you move this one and this one to the other side. You know, y equals to 7 minus x over x minus 4, which is the same thing. It is equivalent there. It's just one fraction versus 2. This is a one. For this one, you're going to have to do a quotient rule here. So if that's the case, then I might as well do the one in red and get the whole thing done at one time. So this is where it works in both directions, as we talked about before on the previous problem. This is one where probably what we have in red, Parker's mistake here somewhere along the way, probably just a mental math error, I'm sure. This is probably the one that I'd actually go with. Because if I'm going to have to do a quotient rule regardless, then I would much rather do an outright quotient rule. Questions here? Concerns here? Okay, now we can keep going and knock out more of these. But what I want to talk about some properties of inverses, which is what's on the next couple of slides. Let's talk about some properties of inverses. So if I give you two functions, one way to double check to see if they are inverses is to evaluate them together, to nest them, to do a composition of functions, f of g of x, or g of f of x. This is a great way to confirm that these are inverses. If they are inverses, plugging one into the other should eliminate all the things, all the operators, and leave us just with an x, because that's what inverses do, right? They should undo what the other one does. Adding and subtracting, multiplying, dividing, derivatives and integrals, right? They're all inverses, so of course this should be no different if I make a more complicated function like fx gx. If I stack them together, but they're supposed to undo one another, then they should just leave me with an x. If this is anything other than this, then they're not inverses. Right? So, oops, what happened there? Let's go to the next slide. Can you confirm for me real quick if these two are inverses or not? You confirm or deny whether or not these two are inverses. I think it's easier to do function composition than it is to find the function, because there's a lot of alternatives sometimes for the way functions can be written. We've seen, even in my most basic examples, there's at least two sometimes. As we look at more complicated functions and more complicated settings, we of course have more and more and more ways we can represent that. So rather than just trying to say, oh, well, f inverse is this when I do the swap and resolve, I think it's a lot easier to go with the composition instead. We don't need to test this in both directions. One would suffice. One would suffice. So we can either go f of g or g of f. If it works in one direction, it will work in the other. If it doesn't, then it won't in the other way either. So you don't have to pick. You don't have to do both. Last year I made them do both, and that became just a train wreck. So we're just going to focus on just doing one. Who'd like to help out? Dawson. Dawson, what did you do, f of g or g of f? what now?
Like F in the G.
F into G, so that would be G of F of X. Right? Like this? Okay, so that means we need the G function, which is our cube root of X plus 1 all over 2, correct?
Yeah.
That's what it has right here. Of course, we're not going to use X. Instead of using X, what are we going to put instead? 2x cubed minus 1. Okay, now we just need to reduce down, correct? As we do so, what's going to happen? 1's cancel, 2's cancel, cube cancels, I'm left with x, right? So G of F of X did in fact equal X, so these are inverses. If you do it the other way around, it should work just as well. Should work just as well. And in fact, it would if you went with the other direction, F of G of X, and plug G into F. The first thing that would happen is the root and the power would cancel. That would allow you access to the 1 and divided by 2, which will also cancel with the multiplier and the minus 1. Questions here? It's actually the same exact steps that Dawson and I took here. It's just in reverse order. The powers cancel first rather than last. Questions here? Issues here? You guys remember doing this in pre-calc? My God, I hope so. It's like unit 1 in pre-calc. It's like, what, day like 3 or 4, I think. These are the same pre-calc slides for the first like 10 or 15 of them. I have not changed them. So those of you that just came out of pre-calc, like Allie and Dom and Todd, this should be extra familiar to you. Okay, can you verify whether or not these two are or not? On to the next slide. Confirm or deny. Okay? What do we think? What's up at? Caleb, what'd you do? F of G or G of F?
G of F.
G of F. So G and then F. Okay, so G's function is x minus 9 over 4. Of course, we're going to go ahead and swap x for our 4x plus 9, correct? Okay? What happens?
The 9's cancel and the 4's cancel.
So I'm looking at x here, so G of F of x is x, right? So are these inverses? Awesome. Questions here? Next slide. What about these two? And then there was 3 to choose from: Todd, Caleb, and Anne Marie. Who's going to do this one? Mr. Carlson going to step into it. I like it. I'll give you another second or so just to confirm, feel good about what you got there. It looks like the rest of our class here looks like they're just about ready to go. So take it away, sir. What are we doing? F of G, G of F. Okay, so g of f of x. Okay, so that means we're going to go to the g function, which is x cubed plus 4. Of course, we're not going to use x, right? We're going to use our f function instead. Cube root of x minus 4. Okay? What happens?
Well, you get like
I'm going to get a monstrosity of an equation. It is going to be horrifying. It is not going to reduce down. This does not just cancel with that one and give us access to this. That's not what's going to happen here. That's not what's going to happen here. The biggest problem there is that that minus 4 needs to be inside that root. That's really what's causing the problem. If the minus 4 was inside that root, this would be a lot better for us and it would work the way we want. But unfortunately, it is not. And therefore, we have a problem. The other fixture, of course, is the plus 4 could be inside the cube power, and that would also make this work. But these are not going to be good exchanges here. Questions or concerns? Okay, so let's move along. Let's move on to our next slide. So, way back when, I also talked about the horizontal and vertical line test. Okay, so a horizontal line test tells you whether or not a function, an inverse function, is possible. So let's be clear about this, because this wasn't super clear last year. I feel like last year in pre-calc, this got muddy. So let's be clear now. You can always create an inverse equation. That does not necessarily mean that inverse equation meets the criteria, the strict criteria to be classified as a function. Okay? A function is a specific class of equations. It is a specific class of equations. So this is telling me when I do my horizontal line test, if an inverse function is possible. An inverse equation will always be there. You can always just swap the two and grind it down. That's just basic algebra. What is not always possible is that inverse equation meeting the same criteria to be a function in return. So just because you have a function to start with doesn't mean that the inverse will also be a function, will also meet that criteria. Does that make sense? Okay, so a good way to test this is the horizontal line test. Now, the horizontal line test helps us test a couple of things here. We have our vertical line test, and we have a horizontal line test. These two things, as you will come to find later on in math classes, are actually referred to as one-to-one and onto. That is what the correct terminology means, is one-to-one and onto. One-to-one means that every x value spits out a specific y value. The vertical line test. Every x spits out one y. Onto works in the opposite direction. Every y has one particular x. So something like a quadratic is one-to-one. It passes the vertical line test. It is a function. It does not pass the horizontal line test, meaning its inverse is not a function because it fails to meet onto. Does that make sense? So vertical line test gives you one-to-one, means that what you're working with right there in front of you is itself a function. A horizontal line test will give you onto, which means that its inverse will also be a function. Later on, if we were able to get there, we would want to specifically focus on functions that are both one-to-one and onto, equations that are one-to-one and onto that pass the vertical and horizontal test. Those types of functions are very useful, very powerful, and there's a lot of features that go with them. Okay? Now, I know that not all of this is on the slides, but that's part of the reason why you're in class, because I can't put everything on slides. And what I just told you is like literally a couple of pages long. So, looking at some of these graphs, when I look at these two right here, the first one which is just your traditional parent graph of a cubic function. This passes the vertical line test. It is a function, which is why it's written as fx. It also passes the horizontal line test, meaning that its inverse, the cube root of x, is also a function. Now, when we look at the one beside it, the absolute value. Absolute value itself is a function. It passes the vertical test, but it does not pass the horizontal test, meaning its inverse is not a function. When I do the inverse equation, it is not a function. The inverse of an absolute value graph is actually piecewise. It's the easiest way to do those. So let's just look at a couple of pictures and let's determine whether we are going to pass, fail the vertical line test, the horizontal line test. Let's talk about what we're going to see, whether we're going to be one-to-one or on-to here, okay? So if a function passes the horizontal line test, it is one-to-one, okay? If it passes the vertical line test, it is onto. I think I might have said those backwards just a minute ago, didn't I? I don't know. Now I'm having a dyslexic moment. Follow the slides. Follow the slides. Okay? So, I know the terminology, I just might have said it backwards. My fault. Hope I didn't confuse everybody. But the meanings still remain the same. One-to-one means every x means that every y has only one x value that creates it. Onto, of course, means that every x creates one singular y. So, how this impacts domain and range, going on to the next slide, is, well, what we do is very simply we switch x and y, right? So that means that your requirements for domain and range should also switch completely. This is important to pay attention to. Why is it important to know what's happening with domain and range? What comes after domain and range? What you learned in math classes, first you start with domain and range, and then what? It starts in math 2. It comes from our first derivative test.
Intercepts.
No, not intercepts. Intercepts don't come from the first derivative test. No, that don't come from our first. Increasing and decreasing intervals come from domain and range. Max and mins, yes, do technically come as a part of that. But what we typically use the first derivative test to tell us is where we are increasing and decreasing. For us to truly know max and min, we have to typically go to the second derivative test. So this is important to us to know. Because if we're switching where x and y are, that means that we are going to alter what's going to happen with our increasing and decreasing intervals. So we're going to talk a little bit about that here. Are we all okay with this slide, talking about domain and range? What slide number are we on here? I just want to make sure that I say that out loud correctly. So we are on slide number 15. We're approaching the end of my notes for today. So let's take a look at a couple of graphs. Take a look at a couple of graphs, and let's do this in a basic sense. Let's start by defining whether or not it is a function. Doesn't pass the vertical line test. And then let's talk about whether or not its inverse will be a function. Does pass the horizontal line test. And then, of course, we will talk about the domain and range. So let's start with this one right here. We have a nice linear graph. It's got a nice slope to it. Got a good y-intercept. Todd did the last one, so Caleb or Anne-Marie, who's going to do this one? Mr. Berg? Is this a function?
Yes.
It is. It passes the vertical test, right? Is its inverse going to also be a function? Yes, it does. Pass the horizontal test. What's our domain and range of a line?
Negative infinity to positive infinity.
negative infinite through infinite, and the range would be the same. So we're looking at a domain and range here where we would have all real numbers available, right? So we'd be looking at the inverse having domain and range of all real numbers available, right? Mr. Bird, one more question. Where's our intervals of increasing and decreasing here? Should be able to look at the graph and just tell me that.
Increasing negative infinite through infinity.
It's the original function is increasing negative infinite through infinite, right? Caleb, think about how domain and range are changing. Will this change increasing and decreasing? Could you tell me that for the inverse now? It shouldn't change because domain and range were the same before. They're going in the same directions together. Therefore, when we swap them, they should still continue to increase as time goes on, right? As your y's are going up, your x's are going up, right? They have a direct variation there together. So if I swap those and make y's x's and x's y's, they're still both going up together, aren't they? Therefore, we're increasing. Questions here? So you kind of see how calculus is going to play back into this when we talk about this. This is going to be unit 3 mixing back in here with your first derivative test. Okay? So yes, the inverse is a function. We gave our domain and range. So Anne-Marie, let's take a look at this one. Take a second, look it over. Are you ready? Okay. Is it a function on its own?
Yes.
Yeah, passes the vertical line test, right? So it is onto. Okay? Horizontal line test, it's inverse. Will its inverse be a function? No, it fails 1-to-1, meaning that every y has more than one x that could generate it. Which, when we look at a parabola there, right? If I look at, let's say, 4, I can see that on the left side and on the right side, there are 2 different x values that make 4. So the inverse here will not be a function. Let's talk domain and range here. Domain of a parabola is, of course, yeah, it's unbounded. It's all real numbers for its domain, and its range here would be -5 through positive. That looks like about -5 to me. Okay. So what would the domain and range of the inverse then be? If you told me the original domain was negative infinite through infinite, and the original range is -5 through infinite. I'll tell you what, let's even go one step farther before we do that. What's our increasing and decreasing intervals here? The parabola does both. What's our increasing and decreasing intervals here?
Decreasing would be positive infinity to -5, and then increasing would be -5 to positive.
Let's try again. Decreasing from negative infinite to what x value?
0.
0. And then we are coming back up from,
0 to infinity.
there we go. Not actually including 0 itself, because 0 is not neither increasing or decreasing. That will be our minimum. Yes? Okay, now let's talk inverse. What's inverse domain? This inverse range. And do you think that we can do these? Let's see.
Would they be flipped?
Yep. So the domain is going to be
Positive infinity to negative
no,
Or flip range of domain.
or flip range over. So this is going to be -5 through infinite. Right? Okay, what's our range looking like?
Negative infinity.
Negative infinite through positive infinite. What do you think about increasing and decreasing it? Any idea, or you just want to leave that be for a minute?
Just
Leave a B for me. Okay. Questions here? Concerns? Okay. What about this? What about this? I'm gonna come back to this one here, Anne-Marie, in just a minute. What about this? Come on, this is easy. Is it a function on its own? No, fails the vertical line test. It's not inverse is not going to be a function either. Fails the horizontal line test. It's a circle, right? Circles are a different class of functions. They're a different class of equations. What about this monstrosity? Is this graph going to be 1-to-1? What does 1-to-1 mean? Horizontal test. Does this pass the horizontal test? No. No, it does not. At like, what is that, 2? We got 1, 2, 3, 4, 5, 6 y values that make 2. That doesn't help us. You guys actually should be able to look at this next graph right here, this monstrosity behind our circle, and you guys should be able to tell me what power of equation this is based on what you did in Math 3. Do you know how to remember? This might be useful for those problems that some of us have struggled with, like, here's my equation, what does my second or third derivative look like? So however many terms you have one more than that as your degree of x. So how many terms we got? We got 1, 2, 3, 4, 5, 6, 7 terms in x here. That means that this would be x to the 8th power. This is x to the 8th power. Which means its first derivative would be x to the 7th power, its second derivative would be x to the 6th power, and so on and so forth, right? This is where some of us have struggled with ones like going back to this parabola here. If this is my first, that means that the next equation, the first derivative would be 1 less. That would mean x to the 1st power, or a line, right? Which means the one after that would not be a line, but in fact just a constant. This is some of the questions that some of us have struggled with in the past. Okay, let's move past this giant monstrosity here. Move past this thing. So, let's take this graph. What do you think? Okay. I only see 1 or 2 of you doing what you probably need to do here. Dom, I saw you typing a little bit. What you doing? Yeah, I think that sounds like a good idea because it does say state at the graph, right? That's what we've been looking at. So, you know, Desmos, graphing calculator. All of us should be moving in some way, shape, or form to do that. Pardon? How unfortunate. Use your phone. What do we think? Let's go to Desmos. I have it open somewhere. Let's plug it in. X to the 3rd plus x minus 1 plus x and minus 1. Here's my graph, what it looks like. Mr. Guida, since I already called on you, we'll make this your problem. Function on its own? Yep. Inverse of function? Okay, does that mean that it's 1-to-1? Yep, it means it's 1-to-1 and onto, because it itself is a function. Its inverse would be a function. Domain range here, sir. Negative infinite through infinite, positive infinite or negative infinite through infinite again, right? Same thing for its inverse as well. It has all real numbers. It is continuous everywhere, is what we would say way back in Unit 1. You remember talking about that? Where we talked about whether a function is continuous everywhere or not, or whether it's continuous on an interval. Okay, so let's talk about continuity. I set Dom up to help me transition to the next slide. So looking at our next slide, what is this now, 18, 19, 21. Wow, moving right along. So some key things to remember. If your function is continuous, then your inverse function will be continuous, provided that, of course, it is an inverse function. So Dom's previous one there was continuous everywhere. Therefore, its counterpart, its inverse function, because it had an inverse function, will also be continuous everywhere. If our inverse is a function, then wherever the original is increasing, its inverse will also be increasing. That goes back to Hilbert-Dawson's earlier, where we looked at that line and said, okay, well, its inverse was also a function, and we said the thing was increasing on the entire interval, and we said its inverse will be increasing on the entire interval. If we go back to Dom's just a second ago, Dom's is increasing over its entire interval from negative infinite through infinite, meaning that as x goes up, y goes up. So if we switch those, well, they're still moving in unison together, aren't they? This works also for decreasing as well. So, looking at one like Anne-Marie's. Anne-Marie's was not an inverse function. It failed the horizontal line test. So while we were able to do this, let's talk about the differences here. Anne-Marie's was not an inverse function. Hers was continuous everywhere. There was no point on the domain that it did not exist. Her inverse is not continuous everywhere. That's become very clear, right? It is not continuous on an open interval. We had very clear indicators of increasing and decreasing here. Her inverse function, gang, is plus minus square root x minus 5. Which when graphed is this. It can't be increasing and decreasing at the same time. The top half of the graph is going up, the bottom half of the graph is going down. So it fails to increase and decrease on the same interval. It's doing both at the same time. So this is why making sure that your function is one-to-one is important. Because then you know its inverse will have all of these things, meaning that I don't have to necessarily run a first derivative test to figure these things out the second time around. The most important one, the last one, is if this is one-to-one, then wherever your original function is differentiable, wherever you can take a derivative, also meaning that you could take an integral, then that means your inverse will also be differentiable at that same value, at that same point. So if at 2, you're differentiable, then that means that the inverse will also be differentiable at 2. There's only one caveat to this, of course, is that when you plug this in, you can't get 0 for the derivative. You can't do this for necessarily max and min values because that doesn't work so well. So this has a little bit of a problem when it comes to the critical values there. We can talk more about that in units to come, as we talk more about why functions are special and why they're important to calculus. So, here's what I want you to do. is let's use some calculus to help us. So I have f and g. They are going to be functions on my next slide. I have f and g as my functions. Now I'm going to specifically tell you that g is the inverse of f. G is the inverse of f. What I would like for you to do is, using the information in the red box, I would like us to figure some things out here. So g's derivative, since it is the inverse of f, is equal to 1 over the derivative of the original with g plugged in. The only caveat here is, of course, that when we do this, we can't get a 0 back. This doesn't sound super duper helpful on the surface. Doesn't sound super helpful on the surface. But it can actually speed up this process. Rather than doing what we did earlier, where we found the inverse equation, that would be our g of x in this situation, right? I started with an fx, so the first thing you would have to do is get its inverse equation, g of x, right? Then you would have to do the derivative of that g of x. What I'm telling you here is you don't necessarily have to do all of that. You can speed it up a little bit. So let's take this next problem as my example. This is the last thing I'm going to show you today. And this is where some of our homework is going to take place with these inverses and what we're going to see here. Okay? So I have f of x as 1/4 x to the cube plus x and minus 1. Okay, so I have two questions. I want to know what is f inverse at x equal -3. I want to know what is the derivative of f inverse at -3. Or at 3, not -3. 3. So two questions here. Are we ready to get started? Now, what do you want to do? What should we do first? This is calculus class. What do you think we're going to do first? Okay. See, we're off to a great start. Mr. Kaufman throws the bone here. We're going to start by graphing this to make sure that we have an inverse function. We're going to start by graphing it to make sure that we are, in fact, 1-to-1. Make sure that we pass our horizontal line test. So let me go back to Desmos here. Luckily, it's almost the exact same as the one that Don did earlier. It just has a 1/4 out in front. And this looks like it's going to be 1-to-1, doesn't it? Okay, so that means that we have an inverse function available to us. How does this help us? Go back to our slides. How does this help us with these two things right here? First one's easy. Right.
You can find what f -1x is at x equals 3, because it should be the same, right?
Yes. How would we like to do that?
Like, you could just look at it on the graph or set the function to 3.
Yeah. So let's expand on what Ryan's saying for those of us not gathering what he might have just said. First, I can't do my little XY switch here, can I? it ain't gonna work real nice. It is not gonna work really nicely for me. It's gonna be very, 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 very difficult to isolate a singular y value if I swap this. If I make this 1/4 y cubed minus y or plus y, that ain't gonna be good, okay? That's gonna suck. So we don't wanna do that. So I can't just create the inverse and call it g here and then plug 3 in. It's not as easy as the ones I gave you earlier, right? So we have to find a different way. Now Ryan's thinking outside the box a little bit. He said, okay, well, I have the original. So let's just find that point at 3. Now you said use the graph. That works. Or, of course, Ryan, we can do algebra. Plug in 3. 3 to the third power is 27 over 4 minus or plus 2. That's going to be 35 over 4. Correct me if I'm wrong here, but this should be 8.75. Are we all okay? Now, Brian, did you actually get it in the Desmos there?
Yeah, it's.
Yeah. Okay, so the easy way to do this, of course, with Desmos, we can go over there. Honestly, what I would do is I'd go up here and click on the little settings wheel, and I'd convert this over to a table, and then I would just plug in 3 and have Desmos spit out 8.75 that way. Okay? It's the easiest way to do it. Awesome. So that's what I have here in my red box. So notice that since f of 2 is 3, then f of 3 would be 2, right? So we use this idea to help us find our first answer. So now I want to set up the formula from the previous page. The reason why I want to use the formula from the previous page is because, once again, we're not able just to get the swap for x, y. If we went back to what we did at the very beginning, right, where we were doing the swap and getting that inverse equation, it'd be super easy to do that and then do the derivative, right? Those were super quick, super easy. We were doing them in about 35 seconds apiece, right? So doing a derivative after that wouldn't be that big of a deal, correct? Okay, but what do we do in this situation where I can't generate that inverse equation? That's where what I showed you on the previous slide is going to be useful. When doing that swap for x, y is not helpful, how do I still generate the inverse, and how do I generate the derivative of the inverse? So let's set up what I have from the previous slide. So what I had from the previous slide, go back here a little bit, is the inverse derivative of x is equal to 1 over f derivative of g of x, or f inverse of x, if you want to put it this way. Okay? Are we all okay with our generic equation here? Are we all okay with our generic equation? Over here I have the derivative of the inverse at x. Right here I have the derivative, and here I have the inverse. Okay? Is that clear to everybody? Like I said, notation and writing here is important. I want to make sure it's clear. Everybody can read it neatly, right? Okay. So, what are we dealing with here? What is our x value in question, gang? 3. Okay. So, the inverse, or the derivative of the inverse at 3 will be equal to 1 over the derivative inverse of 3. Are we all okay with me setting this up? Just swapping out generic x for the specific x in question. Right? Okay. Well, Didn't Ryan just give us that value? Isn't this over here our f of 3? Which we said the inverse then was 8.75, right? Okay, so let's bring our 8.75 over. Why do I have 2? Oh, I know why I have 2. Talk about that in a second. So, I don't want to talk about that in a second, actually. I want to talk about that now. So, what you have right here is the inverse with 3, right? Okay, so let's think about what this means. This means that the original equation has a y value of 3, right? It means that this, in black, would spit out 3, right? Okay, so going back to my equation, go back to my graph, where do we have this? Where do we have a y value of 3? At 2, right? So, that means right here, this part right here, is a y value of 3. What y value of 3? That means that gives us R2. It's using that same idea that Ryan just applied just a minute ago, just at a slightly different point here. Rather than saying, okay, here's my x, plug it in, get a y, that'll be my answer. Now it's, okay, working in the opposite direction. If I know that I'm starting with the inverse value at 3, if that's what's going into the inverse, that would make it the x value of the inverse, which is the original function's y values. Does that make sense? Yes, no, maybe. Some of us are looking at me confused. Some of us aren't looking at me at all, so I don't even know what that means. Other than some of you look like you just want to give up on life. How are we doing? Todd?
So we didn't need that equals.
Well, not really. Has that thrown us off that we did that? Okay. Do you guys just want me to restart this problem from the beginning? Huh? What time is it? Yeah, I got time. Okay, let's back up. All right, going back to the beginning. Here's my equation, right? Here's my equation. First question, what is f inverse when x is 3? Okay, so when x is 3, going into our f inverse function. Okay, so we graphed it, right? That's what we talked about, we graphed it. Okay, so if I want f inverse to be 3, right? That's what I'm plugging into my inverse function. Whatever goes in to the inverse is going to be a y value from the original, right? Whatever goes into my inverse, whenever I go into this, whatever I plug in here, whatever this is actually an original y value, correct? Okay, so when I want this to be, when I ask you for this to be 3, that's what I'm asking you for. I want to know what x made y equal 3. That's what I want to know. Does that make sense now? So, what I'm looking for here is what x value made y equal 3. Because when I'm asking you, even though that this is written in the first problem like it's an x value, it's going into the inverse because that's the notation. So since it's going into the inverse, while it's the x for inverse, that means it's the y of the original. Okay? So, looking at the original y values, what does that pair up with? It pairs up with 2. All right? I am skipping over the first part because I don't have time for all that. So, because that's the relationship there, the original y value was 3, and it paired up with the original x, which was 2. We flip that. Original y becomes x. Original x becomes y. That's where we set this part up. So right here, I have the same question. This is looking at the original y values, or inverses x's, however you want to view that. I'm looking at, okay, when is the original y value 3? Or the inverse being 3. When the inverse gets plugged the 3 in, what's going to spit back out? 2. Okay, the original x value that gives me that is 2. From here, you need to go back to this and create its derivative. The derivative of this is going to be 3/4 x squared plus 1. We are going to take 2 and plug it in. 3/4, 4 plus 1, cancel 3. So, the inverse of derivative at 3 is 1/4. Does that, I hope, clear things up? I hope so, because I'm out of time. It was an easy day all the way up until the last problem. And I think the last problem is more on me than it is on anybody else. I think that I just didn't do a good job with that one. So maybe I'll try to bring a warm-up problem back like this on Thursday so we can just go through a new one and feel good about it again, okay? But in the meantime, let's go ahead, let's pack up, let's grab ourselves a paper towel. That sheet tonight is your homework. We're just doing the first page. We're just doing 1 through 10. Office hours tomorrow. Quiz coming out tomorrow.